We're now going to move into the issue of modelling of the complex faulted bedrock which underlies Glasgow. It's a challenge which we have to prioritise slightly more perhaps than our Dutch colleagues. So over to Alison Monaghan, who's going to talk about big faults, little faults, multi-scalar bedrock modelling in the Clyde Catchment.
Yeah, so in the bedrock geology of the Clyde Catchment, we have a whole range of scale of faults, ones we might term big or medium or little. And what I want to do in this talk is try and summarise lessons we've learnt from the faulted bedrock modelling we've done over many years to what it means as a geological survey about trying to make those models consistent at different scales. So I'll come back to this image I've got here, which is of 4 different model scales from the scale of a whole basin across the central belt of Scotland to a specific site. And in each of these images I've got of the fault of the bedrock models, the faults are always the red discontinuities that you can see. So really the first question we maybe have to ask ourselves is, does it really matter if our models are consistent at a regional scale to a local scale? And it does if we're a geological survey, because as Katie has already said just now, the models we don't make them just because we're building on a particular site or we're looking at one scientific aspect. We make them and they're used for many things, and they're used at different scales, and so they have to be consistent. They're used by the public. And at the same time, we can't expect that a model on this image here, which is in the centre of... Sorry, I'm going the wrong way. A small model covering a small area, which is in the middle of this image of all the different models, bedrock models we've created over the Glasgow catchment, is going to have a lot more detail in it than those which cover the whole catchment. So we can't expect that all those models would be the same. Some have to be generalised. We can't include faults in them all. So the talk is really about how we do that. And some time ago in BGS, we developed a concept which at the time was called lithoframe, and we talked about creating geological models at different scales and what might be incorporated in those models. So in the sort of coloured cross-section image up here, in detailed models which are in the zone close to the surface, we would have a lot of data, we'd have a lot of detail, and as we move deeper and we zoom out, then clearly those models become more generalised. And ideally, when we're working in the geological survey, we might think about either starting with little blocks of very detailed models and then resampling them to make a regional model that was very realistic. Or we might think the other way around. We've got lots of data on a regional scale. We'll make a regional scale model and make sure all our little models fit in with that. But in the real world, it doesn't work like that. When we've been modelling in the geological survey, for different reasons, we've been modelling at different scales. And it's really a challenge to make sure that all those different models are consistent. And the faults, I've picked the faults because the faults really exemplify the issue of consistency in models. Because basically you either include a fault in a model or you don't include it in a model. It's either included or excluded. And so in the Glasgow area, we've got examples of all different scales, and we've just had to make sure as we go along that we've incorporated detailed models into regional models, and we've incorporated knowledge from regional scale models into local models. And when new data's come in and we've had to change our interpretation, that also goes into the cycle. So it's quite complicated, and we've definitely learnt some lessons in how to do it. So I'll just go back to talking about the faults a little bit. So the image, the geological map image, just shows you a little bit about the bedrock geology of Glasgow in a very simplified way. The grey area called the Central Coalfield and the green geology associated with that is a carboniferous basin where there's a long legacy of coal mining and ironstone extraction. And for that area we have a lot of data. It's where there's been a lot of industrialisation and so on in the past. And in the red area surrounding that, the high areas surrounding the city of Glasgow are volcanic terrain of the Clyde Plateau volcanic formation. All these areas are cut by lots of different sorts of faults, and so the image of the model we've got is a catchment scale model, and you can just see the type of faults we have in here. The faults are on numerous different orientations. There's complicated relationships about how they cross each other and how they intersect. And they vary in size from faults that we can see in outcrop that are a metre or so to faults we can see by in mining data and so on that are hundreds of metres of throw. So we've got a huge range of things to deal with. One of my colleagues has worked out that in the CUSP project we've modelled 794 faults. So why are they important? Well, the photograph I've got here is one example of where faults have been important in terms of the geology. It's an image of Bellahouston Park, which is just a couple of kilometres south from here. And the mass of people are the people who came to see the Pope in 2010 at Bellahouston Park, so tens of thousands of people in the park. And you'll see I've labelled an area in the top of the picture, area not used, and it's very clear that the people are all in one area of the park and not in the other area of the park. And there's a good reason for that, because if we go beneath the ground, which is what the bottom image is, there's some shallow coal mining in the area of the park that's not used. And so some work we did many years ago with Glasgow City Council was looking at a hazard assessment for this park. And whilst the area that's not used is completely safe for people to work on day to day, you don't want 10,000 people jumping up and down on it all at the same time when you've got a work coal seam on there. And it's the faults really which bring that coal seam down into the subsurface, deeper into the surface, in the area where all these people are. So faults are important because they obviously compartmentalise the geology into blocks, and that's important when we're looking at things like heat extraction from mines and so on. And the faults are important as well because they can either form barriers to fluid flow, or they can be sealing and not non-sealing and form conduits to fluid flow. So important for hydrogeology and pollution, and thinking about how waters in the old abandoned mines move. And also, where you've got big fault zones, and there are some big fault zones in the centre of Glasgow, there are some big faults, there'll be an influence on the rock strength in terms of engineering properties and ground conditions when you're, for example, making a big sewage tunnel across them. So the data that we used to make these faulted bedrock models, we used a number of different sources. We used borehole data in the way that Katie's shown for the superficial models. We've also made use of the legacy of coal mining that there is in the area. And the image here, I'll try and do this without moving the slides. Right, the image here shows the extent of coal mining. It's called a mine abandonment plan. The spots are spot heights on the coal seam under the ground, and the coloured lines are where we can interpret faults in that mine abandonment plan. We can work out the geometry of those faults in 3 dimensions by looking at the stacked coal seams that have been mined. And we also have the geological maps, obviously, to constrain our models. We've done the modelling in 2 different ways. We've used an interpolative method where we've got lots of data. So the image with the blue surface is an area where there's lots of coal mining data, and that's all the yellow data points that are constraining, in this case, a series of fault blocks stepping down into the basin. And that's been done in an interpolative packaging in GoCAD with some geological interpretation. And then at the other extreme, in the volcanic uplands, we don't have the subsurface data, and we've done a more of an interpretive modelling using GSI 3D and cross-sections. But in each of these cases, we've got a lot of faults of lots of different scales. So just moving on now to think about some of the different models that we've made. I'm going to go from site-specific scale models up to regional. So this is an image of a linear kind of model that we made to go along a major infrastructure project, a major sewage tunnel planned to go on the south side of Glasgow. And it's a complicated model. You can see there's lots of different faults in it, and the different colours represent different coal seams, a lot of which have been mined. And that's within the top 30 metres. So putting a major tunnel through this area is quite a challenge. And obviously at this scale we are including all faults in a model of this scale that we know about, that are proven from data. And we've also done similar models on mine waters escape on a local site, and on subsidence hazard from coal mines. Okay. And then we zoom out a bit to the kind of blocks that Katie showed, the sort of 10 by 10 kilometre block. And this has been used for guiding sort of planning and regeneration in general, for example, by the Council and by the Clyde Gateway Consortium in the east end of Glasgow. And here, the faults in this model we would only include if they were over about 30 metres in throw or 2 kilometres in length. So we've had to not include in this model some of the very small faults because we just can't model them all. And if we zoom out again to the regional scale, then this is the image I showed before of the whole catchment model, all the different orientations of faults. And in the bottom image is an example of the volcanic bedrock model. And in both these cases, we can use this to learn a bit about the development of the Carboniferous basin and when faults moved, when they were active, and how things developed in that basin. So we can get some interesting science out of that. And these sorts of scales of model are important for things like unconventional energy, deep geothermal, and also the regional scale, the hydrogeology. But these would only contain faults over about 100 metres in throw. So going back to my original sort of nested models of different scales, have we made these consistent? Well, we've got sort of rules for inclusion and exclusion of faults based on their size and rules for how faults are dipping and so on. And we've developed a series of procedures really to make sure we're consistent. As geologists, we always like to do what we think the geology is like, but we tried to be a bit more consistent amongst ourselves by reporting what we do, by having a sort of quality control procedure, by checking procedure, and by making sure that all the modelled objects are available for other people to use. And so, has it worked? Well, this is an example where it has worked. In the top of this cross-section, this is a local scale model with lots of coal seams modelled in the different colours and then faults in red. And at depth, this is the regional model where we've only got the one very big fault modelled. But you can see that the structure, the complicated sort of fold structure, so a syncline and sort of anticline that you can see in the local model, which is offset by lots of fault, is replicated but generalised in the regional scale model. So in this case, we have managed to make these models not the same, but they're consistent. So to conclude, doing this bedrock modelling has really given us lots of examples of how to solve these problems and making faulted models consistent. And really, I've used the faults because it exemplifies the problem of whether you include it in a model or you don't include it when you're generalising it. And the main things we've learnt really about making consistent multi-scalar models are illustrated on the kind of star at the bottom, is that we need to document what we've done, we need to write it down, we need to have a quality control system in place, we need to have kind of rules or protocols for how we do things to force the geologist to have some sort of consistent interpretation style so that people don't go wild and have their pet sort of style of interpretation. And within that, it means that people doing modelling really need to know a lot about the local to regional geology and all the data sets that are available. And this is all working towards putting all these models together into a national geological model and holding all these different modelled objects together in a modelled object store. Thank you.
Thank you very much, Alison. The concept there of geologists going bad. Questions from the audience, please? Back there on the phone.
It's great to have this data set of faults. I was wondering, is it possible in the future that they can actually parameterize the faults with a function there that can put properties such as hydraulic properties into this database?
Yeah, you can in the kind of modelling software we have. The problem, I think, is we don't have the data to know what the properties of the faults are often, because it's very difficult to measure the properties of the faults in terms of if they're sealing faults or non-sealing faults and so on. So if you had some data, yes, obviously the packages we use are oil and gas industry sometimes, and so they have that functionality because it's very important from that perspective whether things move along faults or not, so you can parameterize them.
So I just quickly add, we're actually trying to address that issue by doing work in some of the big open cast sites to the south of Glasgow to acquire data that's relevant to that type of parameterization. But, next question. question, Gillian did.
I'm on the world as a planner, and I'm a bit lost. And I just written myself down a question of how do I use this modelling in my work? How can I, because it goes back to what Hickman said, it's very complex. And I almost want a red, amber, green that says, don't jump up and down on this bit.
Well, that's what's...
You're okay here, but you need to do a bit more information. And this is green, it's good to go, it doesn't matter. But it's how are you going to take all that complex information, you've got it for Glasgow, but how are you going to give it to me to use so that it actually has a life? That I can use it in my world, that allows to make my world easier and makes the decision making easier, and makes those discussions that I have with people easier. Because when I'm looking at special planning in the city, it's almost a gut reaction. I know there's tons of mind in the city because I work on the corridor from the geotechnical guys who go and try and find these and try and stop their machines falling down. And very occasionally we end up having to put mesh and stuff, or we lose our machines down there. But it would be nice to be able to have something systematic that wasn't giving away any business secrets, giving away anything, that allowed us to start by saying, and wasn't going to scare the insurance industry, but allowed us to make a decision. Look, lightweight
Have a quick go at that one, Alison.
Yeah, so I mean, I think when we did this work in Bellahouston Park a long time ago, we did just that. We translated the Bedrock model and the superficial cover, and we looked at it and we did a hazard assessment. So we essentially produced a map of different areas of hazard and gave some guidance about what that meant in reality to the use of the land. But what I would say is that the models that we're making as geologists, they're like the building blocks, and they're made for so many different things that we basically wait until somebody comes along and asks us the question. What's the question they want answered? Because there are so many different questions. In the 1970s and 80s, I think, BGS made a set of environmental geology maps which had things like depth to shallow mining and some of these other geohazard things. And I mean, they've proven very successful, so people can come and ask us, and we would make those, but it really depends on the question you're asking, I suppose.
That's a dialogue we will have.
Yeah.
Thank you. We'll have to move on, I'm afraid, Alison, but please continue the discussion.